short module, we will prove basic properties of open and closed sets. The proofs are more or less exactly the same as what we have seen for the real numbers, so we shall be very brief in the proofs. Proposition. Any open ball in a metric space X is open, and the proof is rather trivial, so let BXR subset of X be an open ball let Y be an element of BXR. Now we have to show that this point Y is an interior point of BXR. So what we do is choose R1 by definition to be nothing but R minus dxy, exactly what we did for the real numbers. Then clearly this R1 is greater than 0, and if you consider B, which is just BYR1, the triangle inequality will immediately tell you that B is a subset of BXR. In fact, to see this more precisely, let Z be a point of B, then dxz will be less than or equal to dxy plus dyz, which is less than or equal to r minus dxy plus r, which is equal to r. So this proof was rather trivial. Now we are going to do a different characterization of open and closed sets. We are going to show that open and closed sets are dual notions. So again, the proofs of this is very similar to what we have already seen for the real numbers. So proposition, a set G subset of X, which is a metric space, is open if and only if the complement of G is closed. Okay, so the proof, on to the proof. So what you do is we just define F to be the complement of G in X. Now assume G is open. Now our goal is to show that F is closed. So let Xn in F be a sequence such that Xn converges to X. Okay, we have to show that X is also an element of F. If X is in G, then for some r greater than 0, BXR is a subset of G. That's just because this set G is an open set, therefore X must be an interior point, therefore we can find a ball such that BXR is fully contained in G. Well, this means X cannot be an adherent point of F, a contradiction, right? What will happen is, after a particular stage, we must have Xn is there in this open set BXR. That's simply not possible because BXR is now a subset of G. Okay, now suppose F is closed. then each point x in G cannot, rather I'll write it in a slightly better way grammatically, then any point x in G cannot be an adherent point of F, right? Because F and G are complements of each other. Now the next exercise finishes the proof. So I'm going to leave a very simple exercise for you guys to do, which is exactly similar to what you have done previously for adherent and limit points in the case of the real numbers. So exercise is the following. Let X be a metric space. And let S be a subset of X. Okay. Then a point X in X is a limit point of S if and only if for each r greater than 0 B x r intersect S set minus this single element X is never empty. Okay. In a similar way, X is an adherent point of S if and only if for all r greater than 0 bxr intersect S is non-empty. Okay, these are exactly similar to the characterizations that you have previously seen for adherent and limit points in the context of real numbers. Okay, the final proposition of this short video is the characterization of closures. Okay, so this is characterization of closure. This just says given S subset of X, again a metric space, then S closure is the smallest closed set that contains S. Okay, so there are two parts to this. First is to show that S closure is in fact a closed set, which is if that were not the case, the nomenclature closure is a really stupid name. Second part is to show that S closure is the smallest closed set. So let's go ahead and prove this. So let xn be a sequence in S closure. Okay. Now, since xn's are elements of X closure, we can find yn in S such that dxn yn is less than 1 by n. We can do this because each xn is an adherent point of S. Therefore, we can always do this. Okay. Now, fix epsilon greater than 0. Okay, so I missed a step. Let xn's be elements of S closure be a sequence converging to X in S. Okay, so this is important. So let xn be a sequence in S closure that converges to a point. So again, a slight error again. This should be X in exclusion. Or rather, again, this should be just X in X. Our goal is to show that this X is actually an element of S closure, which will prove that S closure is in fact closed. So fix epsilon greater than 0, we can find n so large that simultaneously 1 by n is less than epsilon by 2 and d xn x is also less than epsilon by 2. Then a trivial application of the triangle inequality would tell you that dy n x is less than epsilon. Consequently, yn converges to x, and this means x is an adherent point of S, which means X is in S closure. This shows that the closure of a set is always a closed set. So this concludes this video on basic properties of open and closed sets, and you're watching this course on real analysis.